So the next field we need to study is called dynamics. Dynamics is the study of forces in motion. Forces and how they make objects move. So to understand this, we first need a good definition of a force. And a good, very, very simple, the most basic definition would be that a force is a push or a pull on an object. And the purpose of this force is to cause some kind of motion, which doesn't always happen. Now, the units of forces are named after the guy that really brought forces into the standard realm of science, a guy named Isaac Newton. So we call for the units of force the newtons. And the reason we do this is because Newton kind of came up with three laws that came up that kind of govern how forces actually work. So Newton's three laws of motion start with one, the law of inertia. This tells us that an object in motion stays in motion, object at rest stays at rest, unless an outside force acts. Equation number two, Newton's second law, tells us that the sum of forces acting inside of a system is equal to the mass times the total acceleration in that system. We've seen this equation before. We've seen it in the form of weight. Weight is just equal to mass times the acceleration due to gravity. Weight is just a force. It's equal to the mass times a, which is the acceleration due to gravity. So weight is a statement of Newton's second law. And finally, we have every force has an equal and opposite force. So when I push on something, it pushes right back with an equal and opposite force. Now, specific forces that we need to get familiar with have some specific names. In particular, we want to get familiar with the normal force and with another force called tension. These are the two that we'll start with. So the normal force is a perpendicular force due to surface contact. So anytime an object is sitting on top of another object, it experiences normal force that's perpendicular to whatever surface it sits on. So we can draw a picture of what this looks like. I can take a box and just put it on a floor. Physicists are obsessed with boxes on floors. And we can identify the forces. We can draw a picture that represents this. It's called a free body diagram. And I can identify where all the forces go. Here's my box. I see gravity is acting to pull it down. That's why it doesn't float away. So we have some weight equal to mass times gravity. According to Newton's third law, there's an equal and opposite force pushing straight back. That equal and opposite force is going to be the normal force. Here I label it with F sub n. In some places, you'll see it labeled with just an n to represent the normal force. This can get a little confusing if you're working with Newton, so I prefer to use this F sub n diagnostic. So we can also have a box on an incline. Physicists are also obsessed with putting things on inclines. So here's my box sitting on a slant, sitting on a ramp. I can identify the forces. I still have Earth pulling it down with some gravitational force. Some weight equal to mass times gravity. Now I know there's also going to be a normal force, which is perpendicular to whatever surface you're sitting on. That normal force is now not straight up because I'm on an incline. It's perpendicular to that incline. So I need to draw a right angle to the incline and draw my force going perpendicular. So there's my normal force for sitting on a surface. Now, the other force specifically that we need to get familiar with is tension. The force of tension is basically the tautness inside of a rope. Whenever you hang something from a rope, it feels some tautness. It feels some tenseness. So here I have a little ball hanging from a rope. Again, gravity is pulling it down. That's why it has some mass. And then there's an equal and opposite force from Newton's third law acting straight back up that string, straight up that rope that makes it tight, that makes it taut. And that tightness, that tautness is your tension. So how do I actually solve problems involving this? Well, first, we need to draw a picture. I have, let's say, a box sitting on an inclined plane. I'm going to attach a rope to this box and have a person actually pulling on this rope to drag this thing up the inclined plane. So the first step in any kind of force problem is to draw a picture. And in that picture, you want to label all your forces. So this is no different than any problem in physics that we've already done. We basically follow the same procedures, it's just labeling different things. So to label those forces, we can first recognize right away that we have this rope. And inside of this rope, we're going to have tension. So we can draw the tension in. I have tension acting straight up on that rope. And then I also know I have a normal force because I'm sitting on the surface of this incline. So I have a normal force that acts straight up. That normal force is perpendicular to my tension. And then last of all, we know we have gravity that's acting straight down. And something I need to notice is I don't have a normal coordinate system here. I don't have a very useful coordinate system. Because normally, we have everything acting to the left and right and up and down. These are our normal x and y axes. In this case, what I want to do is I want to rotate this x and y axis some angle theta that's equal to that incline. So instead of x and y being horizontal and vertical, they're going to be along the incline. So I'm going to have new x and y axes. So let's draw those in a slightly different color. I'm going to have an x and y axis. So I'm going to have a y axis that's perpendicular to my incline. That's my new y. And I'm going to have an x axis that's parallel to my incline. Turns out this is a good choice of coordinate system, and it's a perfectly valid choice. So what I have to do now, though, is recognize that my gravity is no longer acting along these directions of these new inclines, of these new coordinate system. So I need to kind of decompose it into a right triangle. So I put a piece of it that's going in the y direction. That's going to be FGY. So this is a very similar process to what we use in projectiles, where we break up the force into x and y components. Except this time, we've kind of rotated our x and y components to be along this incline. So I have these new components, and then I can actually start labeling the forces and write these sum of force equations that govern how this problem, how these forces are going to interact with each other. So I can write the sum of forces, according to Newton's second law, is equal to the mass times the net acceleration in a given direction. So I can do the same thing I do with projectiles and do things in the x direction and things in the y direction. Now in the x direction, I have a sum of forces acting in the x direction. That's going to be equal to tension, which is pulling me up the incline. And I'm going to say that anything going up the incline will be positive. And then if I look at what's going down the incline, I don't see anything directly anti-parallel to the tension. But if I shift my view a little bit down, I can see that my force of gravity in the x direction is pulling this thing down the incline. Gravity is acting against you. So I have tension minus the force of gravity in the x direction, and that's got to be equal to the mass times the net acceleration. And I can further break this up into tension minus FGX, where FGX is going to be related to this angle of the incline. And it turns out that with my new coordinate system choice, we can geometrically show that the angle of the incline is equal to this angle right here in the new coordinate system triangle I've drawn. So my coordinate system gives me that my force of gravity in the x direction is directly opposite of that angle. So that means it's going to be equal to F sub g times the sine, because it is opposite of that angle, that theta, equals mass times the net acceleration. So there's my sum of forces in the x direction. I could do the same thing in the y. Sum of forces in the y direction, I'm going to have acting perpendicular to this incline. So perpendicular. Acting up, I have the normal force. And then acting down, directly opposite, I have FGY. Now the other tricky thing about these kinds of inclined plane problems is looking at the motion of where this thing is moving. So this thing is moving up the incline. It's moving entirely in the x direction. It's moving just along this incline. It's not moving at all perpendicular. So that means that the acceleration that I experience perpendicular to the incline has to be equal to 0. So this is equal to m times a in the y direction, the net acceleration of that, and that is going to be 0. Since this is just moving up and down the incline. It's not moving perpendicular. It's not bouncing around as I'm moving it up this incline. So I have my normal force minus my Fg times my cosine of my angle, where I'm using cosine because I am now adjacent to this angle that I start at, equals 0. So the normal force equal to, so I got a little bit cut off, but all we needed to make note of was that the normal force is equal to m times g times cosine of the angle. Okay, so that's how we the approach we're going to kind of use to solve force problems. And the last thing to make note of for forces is kind of a more big picture view of what's going on with force. And the big picture view is that there are 4 fundamental forces out there in nature that all act at different scales. The first fundamental force is something called the strong force. This is the strongest force that exists in nature, that exists in physics. It exists to hold the nucleus together. And there's a little carrier or gauge particle, we call it, that actually holds the nucleus together. We call this the gluon. Second force in nature is the electromagnetic force. We'll get into this in other semesters, other kinds of semesters of physics. The electromagnetic force is what's responsible for light. And light is carried by these little particles called photons. So that's how light gets around. We also have something called the weak force. The weak force, we kind of see this in radiation, in radioactivity. So this is how the Hulk gets his superpowers, maybe. And it's carried by the W and Z bosons. We see this all the time in fusion furnaces, in nuclear reactions, and nuclear reactors. We don't have much experience with it on a daily basis, but it's out there. And then finally, we have gravity. Gravity is the one that we're all the most familiar with. I'm just going to describe this as the Daw force, because if you don't know what gravity is, then you probably shouldn't be in college. And then we also have, this is carried by something called a graviton. And a graviton is purely theoretical at this point. We still have not found a graviton. And one of the big things that current physicists are working on, a big new problem, is that maybe these 4 forces are just manifestations of a single force. That when the universe first started, these were all bundled together and they all acted the same, and they've gradually split out over time. So this is a big goal of physics called unification, to make all the forces unify together.